Good morning, students. In the last class, we discussed the topic optical instrument. In that, we studied simple microscope and compound microscope. That is, microscope is used to see the point size objects in a larger size. That is, magnified size. So, in today's topic, we are going to discuss one more optical instrument. That one is telescope. So why we are using the telescope? So telescope is an optical instrument which are used to see the distant objects. That is the objects which are far away from us. To see that object, we are going to use the telescope. So telescope is an optical instrument that one we use to see the distant objects. That is distance object, nothing but the objects are far away from us. That is up to the distance may 100 kilometers or 1000 kilometers or lakh kilometers. From that distance we can see the objects. So that is the telescope. Next, construction of telescope. As similar to the compound microscope, in the telescope also we have two lenses. We are going to use the two lenses. So one is the objective lens of focal length, so this one is the objective. So it has focal length f(O), and another one is its aperture is greater compared to that of eyepiece. Aperture nothing but the diameter of the lens. The diameter of the aperture, that is diameter of the objective is more. So another lens we have taken here is this one we call as eyepiece. So the lens which is nearer to the eye, that lens we call as eyepiece. So this aperture is very small. Focal length is also small. So objective focal length is f0 and eyepiece focal length is taken as fe. So this one is the axis. And the objects are far away from us. The objects are far away from us. From that object, the light rays which are coming are parallel to the objective. The light which is coming from the object all are parallel. So the light rays which are coming from the object, that is distant object, those light rays are parallel to the objective. So in the lens, if the light rays are parallel, then after refracting the incident rays are meet at the focus. The parallel rays after refracting they converge at a point. That point is the focus point. Then if you observe here, so this is the optic center of the objective lens. So these rays are parallel rays which are coming from the distant object. When the parallel rays incident on the lens After refraction, they converges at a point. So here we get the point. At the convergent point, we get the image of the object. We get the image of the object. This one is B dash and here it is A dash. B dash and here it is A dash. So this one is the image of the distant object. So the light rays which are coming parallel and incident on the objective and its image, because the parallel beam which incident on the objective, the refracted rays or converges. The converging point gives the image of the object. So here I am taken A dash B dash as the image, that is the object is AB. That one is at a far distance, that is almost, if we compare up to larger distances. So from there the light rays are coming parallel. Here we get the image of the object. Later, as we already discussed in the compound microscope, the image formed by the first lens acts as the virtual object for the second lens. Here the image A dash B dash acts as the virtual object for the eyepiece, that is for the second lens. From here, again which are incident on the right. So this image acts as the virtual object for the eyepiece. This eyepiece is adjustable, that is, it has to be, we can move either forward or backward. The eyepiece is adjustable. We adjust eyepiece such that this image is to be placed on the focus of the eyepiece, because we have to get the image obtained by the eyepiece is at infinity. The condition for V is equals to infinity, that is image obtained by the eyepiece is to be infinity, then the object must be focused at focus, that is principal focus. So this virtual object has to be placed at the focus of the eyepiece. So that is the distance from eyepiece to the image is Fe. So when the object is at focus, then the image we get is infinity, at infinity. So image we get So if the image is formed at infinity, then we get the clear picture of the image. That is, we have clear picture of the object. That is, image we getting at infinite means that image is very clear. So here the distance from here to here is FO, because the parallel rays which are incident on the objective or convergence at the point which is at focus. that is f naught, that is the distance from O to B dash is f naught, and this eyepiece is adjusted in such a way that the image, that is the real image formed by the objective, is to be placed on the focus. This real image acts as a virtual object for the eyepiece that must be placed at focus, then we get image at infinity. If the image is formed at infinity, then we get the clear image of that object. So this is about the telescope, construction of the telescope. Here we are taken one angle, that is alpha. Here the angle is alpha, then here also the angle is alpha because of opposite angles. And if we draw one parallel ray at E, that is parallel to the refracted wave, like this. So this ray is parallel to this one. So here the angle formed we taken as angle beta. So in the telescope we are getting angular magnification. Angular magnification. Angular magnification. So angular magnification means the angular magnification of the telescope is defined as it is the ratio of angle subtended by the final image at the eye, that is angle beta. So it is defined as angle subtended by the final image. So this one is the final image. So this final image makes an angle beta with the axis. So this angle beta is called as angle subtended by the final image at the eye. So this one is the eye. At the eye we have beta angle, that is image. This image is subtended angle with the principal axis. That angle we taken as beta. Then angle subtended by the object at length or eye, that is angle alpha. So here somewhere is the object. This object makes angle alpha with the principal axis, that is object makes angle with the axis. That angle we taken as alpha, and the image, the final image which makes angle with the principal axis, that angle we taken as beta. So here the ratio of these angles we call as angular magnification or magnifying power of the telescope. So magnifying power of the telescope is defined as it is the ratio of angle subtended by the final image at eye, the final image. So here it is somewhere at infinity we get the final image. So that image makes angle with the principal axis, that one we taken as beta, and the object which makes angle with the principal axis, that one we taken as angle alpha. So these two ratios, that is ratio between beta and alpha, gives the magnifying power. So from the geometry we taken the triangle O B dash A dash, O B dash A dash, then tan alpha is equals to opposite by, so this one is the opposite. If we take height of the image as hi, so that is equals to, from the triangle O B dash A dash tan alpha, that is equals to tan alpha, that is equals to hi by f, opposite side by adjacent side. So here the angle is very small. For small angle, then alpha is equals to hi by fo. Similarly, from the triangle E B dash A dash, so this is from triangle O, B dash, A dash, and from triangle E, B dash, A dash, tan beta, that is equals to, here I am taken HI. So this image acts as the at infinity opposite side by adjacent side. So adjacent side is B dash E, that is F E. For small angle, beta is equals to HI by F E. So from the definition angular magnification, we have M, that is equals to beta by alpha. So we have beta HI by FE, HI by FE whole divided by HI by FO. So if we simplify, we get M is equals to FO divided by FE. So this is the magnifying power. FO, that is focal length of the objective to the focal length of the eyepiece. So in telescope, focal length of the objective is greater than focal length of the eyepiece. In compound microscope, focal length of the objective is less than focal length of the eyepiece. The distance between the objective and to the eyepiece, that one we call as length of the telescope. So length of the telescope, that is L, that is equals to FO plus FE. FO plus FE. So L is the length of the telescope. That is the summation of focal length of the objective and to the focal length of the eyepiece. That gives the length of the telescope. So this is about the telescope. So we have two lenses. One is objective lens and another one is eyepiece. Objective, the focal length of the objective lens is greater than the focal length of the eyepiece, as the rays which are coming from the distant, very large distance, so the rays are parallel to the objective. So these parallel rays after incident on the lens, then these refracted rays are converging. So the convergence at the point gives the image of the object. That image we taken as A dash and B dash. So this image acts as the virtual object for the second lens, that is for the eyepiece. So this eyepiece can adjust in such a way that so this object is placed at focus. So if the object is at focus, then image is formed at infinity. So when image is formed at infinity, then we get the clear image of the object, that is magnified image of the object. Next, we have angular magnification or magnifying power of the telescope. It is defined as the ratio of angle subtended by the final image at eye to the angle subtended by the object at the lens, at this lens or at the eyepiece. So that ratio is M is equals to beta by alpha. So if we substitute the values of beta and alpha, we get the magnifying power of the telescope, that is M is equals to F4 divided by Fe. So next, the length of the telescope. The length of the telescope is equals to the summation of focal length of the objective and to the focal length of the eyepiece. So this is about the telescope. So next, in the telescope we have another one is reflecting telescope. That one also called as Cassegrain telescope or reflecting telescope. So why we are going to use the reflecting telescope instead of normal telescope, that is astronomical telescope or terrestrial telescope? reflecting telescope. To overcome the disadvantages of the terrestrial telescope, we are using the reflecting telescope. So what are the disadvantages of the telescope? So in telescope, we are using the objective lens which have higher aperture, that is larger aperture nothing but the diameter of the lens. So if we are going to use the larger aperture, then the size of the telescope becomes more and it becomes heavier to place the stand. So this is the main disadvantage of the terrestrial telescope, because for the clear image we have to use the objective lens, that is for larger size. That is, we have the relation magnifying power m is equals to f4 divided by fe. If we want to increase the magnifying power of the telescope, we have to increase the focal length of the objective lens, and we can decrease the focal length of the eye lens. So the main factor is that we have to increase the focal length of the objective lens. Then if we are going to increase the focal length of the objective lens, then it becomes larger aperture. Then larger aperture has bigger size and it has more weight, and it is very expensive to construct the lens to overcome the chromatic aberration. Chromatic aberration. So aberration means it is the defect in the lens. Aberration means it is the defect in the lens to form the image which is not in clear. If the lens, if we consider this one as one lens, this lens has aberration means it has the defect. This lens has the defect. It won't give the clear image of the object. So in that we have chromatic aberration. Chromatic aberration means the rays which are parallelly incident on the lens. After refracting, these refracted rays are not meet at point. That is, it fails to focus at single point. So here this aberration we call as chromatic aberration. That is, the incident rays which falling on the lens after refraction, the refracted rays are not meeting at one point. That is, either in a small changes here, either forward or backward, they meet not in equivalent. That is, they are not meet at one single point. That aberration we call as chromatic aberration. To overcome this chromatic aberration, that is, we have to construct a larger aperture lens. That lens becomes very expensive. So these are the disadvantages of the terrestrial telescope. To overcome this one, we are using the reflecting telescope. In reflecting telescope, instead of lens, we are going to use the mirrors. In mirrors, we don't have any chromatic aberration. In mirrors, we don't have any chromatic aberration, and it is smaller in size compared to the telescope. It is, if the mirrors are very smaller, then its size is very less. So that's why we are going to use the reflecting telescope. To overcome the disadvantages of the terrestrial telescope, we constructed the reflecting telescope. In reflecting telescope, instead of lens, we are going to using the mirror. Construction of the reflecting telescope is we have one concave mirror with small hole in it. Here this lens becomes the eyepiece. So this one is the concave mirror. This concave mirror has small hole. That hole we can place one eyepiece. So this lens is called, so this is the mirror. This one is the concave mirror or objective mirror. Objective mirror. So this one is the first mirror. So inside we are placing one more mirror, that is convex mirror. So this convex mirror is called second mirror. So as the light rays which are coming from larger distance, that is the light rays are parallel. The light rays are parallel. So these light rays are first incident on the concave mirror after reflecting. Here, when the light rays parallelly falls onto the concave mirror, here the rays are reflecting. These reflecting rays are meet at the point focus. So before the reflecting rays are meet at the point to the focus, we place one secondary mirror. We place one secondary mirror, that is convex mirror. After incident on the convex mirror, so the rays are reflecting and meet at the eyepiece like this. So first the rays are coming from larger distance. So these are the incident rays. These incident rays are falls onto the concave mirror. Concave mirror, the parallel rays which are incident on the concave mirror will meet at the point that is at focus. Before the reflecting rays are meet at the focus, we placed one more mirror. That mirror is the second mirror. So this second mirror is the convex mirror. After incident, these reflecting rays after incident on the convex mirror, so these rays will meet at the eyepiece. Meet at the eyepiece. So this is about the construction and working of the reflecting telescope. So here also the magnifying power m is same, that is m is equals to f4 divided by fe. That is focal length of the objective mirror to the focal length of the eyepiece. So this is about the reflecting mirror. So the advantage of the reflecting telescope, the advantages of the reflecting telescope is, here we don't have any chromatic aberration and its size is very small. So these are the advantages of the reflecting telescope. So this is about the topic optical instrument. So in optical instrument we have studied two microscopes and two telescope. So one is simple microscope and another one is compound microscope. So here one is terrestrial telescope and another one is reflecting telescope. In terrestrial telescope, refraction takes place. In reflecting telescope, reflection takes place. So this is about the topic optical instruments. So from microscope and telescope, we can solve few problems on this topic. So the first question, a man with normal near point for human eyes it is 25 centimeter, reads a book with with small print small print using a magnifying glass, using a magnifying glass, a thin convex lens, a thin convex lens of focal length 5 centimeter. So in that first one we have to find is what is the closest and farthest distance at which he should at which he should keep the lens from the page so that he can read the book he can read the book so that he can read the book when weaving through the magnifying glass. Magnifying glass. So in that second one, what is the maximum and minimum? What is the maximum and minimum angular magnification? Angular magnification possible using Yabbo microscope. So the given question is a man is viewing normal near point, reads a book with small print using magnifying glass. So the person reads a book by using the magnifying glass. So that magnifying glass is the thin convex lens and its focal length is 5 centimeter. So the given focal length is 5 centimeter. Next, what is the closest and farthest distance at which he should keep the lens from the page so that he can read when viewing through the magnifying glass? That is, we have to find out the distance of the object to the thin convex lens so that he can view through he can read the book. So the given focal length that is 5 centimeter and the man with normal near point is 25 centimeter, that is V is equals to 25 centimeter. Then we have to find, here we have two cases, one is at closest and another one is farthest. For the closest the image distance is v is equals to 25, and for the farthest the image distance is at infinity. So the given focal length is plus 5 centimeter, and for the first case, that is the closest, for the closest distance we have v, that is equals to minus 25 centimeter, minus 25 centimeter. Then from we have thin length formula for convex length, that is 1 by v minus 1 by u, that is equals to 1 by f. So here 1 by v is minus 25 minus 1 by u, and the focal length given is 5 centimeter. The focal length given is 5 centimeter, then it is 1 divided by 5. So if we shift here 1 by u, that is equals to minus 1 by 25 minus 1 by 5. That is 1 by u, that is equals to, the LCM here 5 and 25 is 25, that is minus 1 minus 5, that is minus 6 divided by 25, then u is equals to minus 25 by 6. So u is equals to, it becomes minus 6 4s are 24, 1 remains, that is 1, 4.1, or approximately it becomes 4.2 centimeter. This one is the closest distance object, that is the distance between the object and to the convex lens. So u is equals to minus 4.2 centimeter. So next is for the farthest distance. Farthest distance v is equals to infinity. So all are remaining same, that is 1 by v minus 1 by u, that is equals to 1 by f, that is 1 by infinity minus 1 by u, that is equals to 1 by, so the focal length f is 5, then u is equals to, so 1 by infinity is 0, 1 by u is equals to minus 1 by 5, that is u is equals to minus 5 centimeter. So this is the object distance for the farthest distance, that is the distance between the book, that is the distance between the page and to the convex lens. So this is the convex lens, and he is reading the, so this one is the page. From page to the convex lens, for the farthest distance is equals to minus 5, and for the closest distance u is equals to minus 4.2 centimeter. So in the second question, that is option, that is second question B, what is the maximum and minimum angular magnification possible with the above microscope? So angular magnification is nothing but magnifying power, m is equals to, so this one is the simple microscope. For simple microscope, the angular magnification m, that is equals to d divided by u. If the object is placed at, if the object is placed at focus, then it becomes d divided by f. We have two cases, one is minus 4.2 and one is 5, that is one is maximum and minimum. We have to find the maximum and minimum. So m maximum, that is equals to d least distance distinct vision is 25 divided by u. Here I am taking u1 and u2. So u here is also u1. Then the value of u, first case for maximum, it becomes 25 divided by 6. So 25 get cancels. We get magnifying power. Maximum magnifying power is 6. That is D divided by U1. And for minimum magnifying power, so M minimum that is D divided by U2. So D is 25 divided by U2 is 5. So magnifying power minimum that is equals to 5 5 is 25. So it is 5. Maximum is 6, magnifying power and minimum is 5. So next move on to the second question. So this is the problem on simple microscope. Next, second version is a compound microscope. A compound microscope. A compound microscope with an objective. With an objective of 2 centimeter. Of 2 centimeter focal length. 2 centimeter focal length. And an eyepiece. And an eyepiece of 4 centimeter. And an eyepiece of 4 centimeter focal length. Has a tube length of tube length of 40 centimeter. Calculate the magnifying power. Calculate the magnifying power. Calculate the magnifying power of the microscope. Of the microscope. If the final image is formed at near point of the eye. Near point of the eye. So this is the problem on compound microscope. So the given compound microscope with objective of 2 centimeter focal length. The given objective focal length is 2 centimeter and eyepiece focal length, that is Fe is equals to 4 centimeter and has tube length is 40 centimeter, that is L is equals to 40 centimeter. Then calculate the magnifying power of the microscope, that is M. If the final image is formed at the near point of the eye, that is near point of the eye is least distant distinct vision, that is D value. D is equals to 25 centimeter. Right? So we know the formula for magnifying power of the compound microscope, that is M is equals to magnifying power of the compound microscope, M is equals to L divided by FO 1 plus D divided by Fe. So this is the magnifying power of the compound microscope. That is the image is formed at nearer point. If the image is formed at infinity, then it becomes L by Fo into D by Fe. Here the image is formed at nearer point. Then M is equals to, the value of L is 40. Focal length of the object is 2. 1 plus least distant distinct vision is 25. Focal length of the eyepiece Fe, that is 4. So here 2 ones are 2 20s are, that is 20 into, if I take LCM, 4 plus 25, that is 29 by 4. 4 ones are 4, 5s are, then 5 into 29. So 5 nines are 45, 5 twos are 10 plus 4, 145. So the magnifying power M is equals to 145. So it's simple problem, but we have to know the formula. So the formula M is equals to L divided by F naught into 1 plus D divided by Fe. They given if the object is, the image is formed at the nearer point. If in case the image is formed at infinity, we have to change the formula, that is M is equals to L by F naught into D divided by Fe. So in the next class, we discuss few problems on telescope and later discuss the previous year question paper problems. Thank you.